Hi, all. Welcome to the 8th session of our Biostats Made Simple webinar series under the Research Learning series. My name is Christine Ramdin. I am a faculty member on the research track at Rutgers, New Jersey Medical School, Department of Emergency Medicine. Very exciting. Today we're at our 8th session. And it has been a wonderful last couple of months, just seeing you all here, different attendees every single time. I keep on going on YouTube and looking at the viewership, and it's just amazing how many people view these videos. And I'm just so glad to contribute to this wonderful effort that'll help accelerate abstracts, publications, etc. moving forward. I've noticed there were a lot of views on the first video in particular, and it started dwindling after the first. I realized that some of this could be very intimidating, but I do encourage you to continue watching some of the videos, even if it's just at the beginning. The way we designed this is so that the first 10 to 15 minutes, we recap on what we previously discussed, and sometimes it just rolls over from other sessions. And the rest of the video is new concepts. So it's okay to just start looking at the video because likely it's like a repetition of something we talked about already. It's aimed to be less intimidating, and the goal is to help everyone. Thanks all for the great, wonderful turnout today. We're going to be talking a little bit about regression models, a continuation from last time, and introducing some new models in this webinar. Just a full disclosure, the talk is not meant to be fully disclosive of all types of regression models. There's just too many to talk about, especially in a Biostats Made Simple webinar series. But the goal is that, the foundation of whatever I talk about today will help you get to the more complicated models if you need them, like the hierarchical logistic regression, etc. I'd like to thank SAEM, Lane, and Lynn for allowing me to do this. I'm going to post the slides right now in the chat. These include slides from our previous sessions, so they're there for your accessibility and for your review in case you want to repeat any mock examples, etc. I noticed there's a lot more of us in this session than there was in last session. So instead of, if there's questions, I would highly encourage you to put them in the chat. Between sharing and unsharing screens, if I catch questions, I'll be able to answer that. If not, we'll be able to knock it out at the end. In total, we plan to have about 10 sessions. Next session will be the 9th session, where we will discuss essentially application of a lot of the concepts we did in previous webinars to an actual big data set, probably by the CDC or SAMHSA, etc., using SPSS. So you guys can see how that's done and you can start brainstorming ideas for your own research studies. And in the last webinar, the goal is to have a guest speaker, and we'll disclose more details about that soon. But that is the plan going forward. So it's been a pleasure hosting you all, and I hope that whatever I've done, whatever we've done together, helps make an impact. And with that being said, I'm going to share my slides and we're going to start this. So our agenda for today is as follows. We're first going to do a recap of this concepts we discussed in last session, which were essentially related to the types of regression analyses that could be done by variable type. As I've said in the previous webinars, there are generally 3 variable types, and this is recognized by SPSS. They are nominal, ordinal, and scalar variables. And just understanding what these variables are can help you determine what statistical test to use, as well as what type of regression model to use. Once we do the recap of what we discussed in the last session, which was focused on regression models for scalar dependent variables, we're going to talk about the types of regression analyses we can do for nominal dependent variables, followed by ordinal dependent variables and count variables, and then we'll do a summary of everything we've spoken about. So this is the agenda for our recap. We're first going to quickly recap on the different types of variables there are. Then we're going to talk about the type of regression analyses discussed up until now, which are linear regression, multivariate regression, and the general linearized model. So in general, there are 3 types of variables. There are continuous and scalar variables, nominal variables, and ordinal variables. Your continuous and scalar variables are like your numerical variables that can take on decimal points, such as weight, height, time, distance, etc. Nominal variables are variables that have categories within them, such as race, gender, ethnicity, etc. Ordinal variables are your variables that, like, for example, your Likert type skill variables, they take on some type of order, as in the name. So in a lot of our medical education research, we ask students to rate their satisfaction with the course, for example, on a scale from 1 to 5, with 1 being not satisfied at all and 5 being very satisfied. So that's a type of ordinal variable. So up until this point in our last webinar, we specifically discussed the type of regression analyses or association analyses you could do for cases where you have continuous or scalar dependent variables. And these are your general linear regression, your multivariate or multivariable regression, and your general linearized model. So when you're doing your general linear regression, you have exactly 1 dependent variable and 1 independent variable. You think about, just plotting points on an X and Y axis, and you want to see whether there is a linear association or not. And this is essentially can be called like a correlation analysis. You want to see if your X and your Y variables are associated or are correlated. So as many of us may remember back, and this is one of the most simple types of association analyses that we've learned in probably elementary school, high school, etc., and it keeps on following us, is the analysis that produces our Pearson correlation coefficient, right? And you do that kind of analysis when obviously you have, again, a continuous dependent and independent variable, such as height and time, etc. But the catch-21 is that both of these variables have to be parametric or normal in order to use the Pearson's correlation coefficient. And in order to test data normality, as we've discussed in several previous webinars before, we have to use something called the Shapiro-Wilks test. So the first step is to conduct the Shapiro-Wilks test, determine if both the X and Y variables that you're trying to associate are normally distributed. And if they are, then you can apply the Pearson's correlation coefficient test, or the linear regression, whose output is the Pearson correlation coefficient, to tell you how strongly those 2 variables are correlated with each other in a linear fashion, and whether that association is statistically significant or not. The other piece to this is that when we have the case where both of at least one of the independent or dependent variables are not normally distributed, meaning they fail the Shapiro-Wilks test, you would have to use another type of association analysis whose output is Spearman's row. And I would just call it the Spearman's row analysis, because when we go into SPSS, under bivariate correlations, you just check off Spearman's row and you hit OK. And it provides you with a coefficient just like the Pearson's correlation coefficient. And it provides you with a p-value to tell you whether that correlation, whether it's weakly or strongly correlated, and whether that correlation is statistically significant. Just a reminder, these coefficients range from essentially -1 to 1, where -1 means a very strong negative association between the variables, and 1 means a very strong association. For Pearson's correlation, that interpretation would be a strong linear correlation. For Spearman's row, that interpretation would be there's just a strong increasing correlation. So when you do this analysis in SPSS, this is the output you get. And what I'm going to do is, because since we have a lot of new viewers, I'm just going to stop sharing right now, and I'm going to share SPSS so I can just quickly show you guys what this looks like in SPSS for those that haven't used SPSS before. All right. So this is what my data looks like in SPSS. All I did was copy and paste my data from my Excel document into SPSS. As I say in all the previous webinars, SPSS does not function like Excel in that it only takes data in a certain format and will only analyze the data in a certain format. Like, it has low tolerance for things like strings. So you want to make sure that your data is perfectly in the format you want it for analysis purposes when you put it into SPSS. The other piece of it is that if you put data inappropriately and you try to run the analysis, you might get an error, etc. So in summary, SPSS is just good for analysis. It's not good for data manipulation. Any data manipulation you should do it in Excel. And then when that data is ready, it should be put into SPSS. Also note that, the data I put into SPSS is coded. right? Like for example, gender, I have male labeled as 0 and female labeled as 1. And then if you go to your variable view, I'm clicking at the bottom here. So in the variable view, that allows you to name your variables, because unlike Excel, where you can just type in the first row that, this stands for age, you cannot do that in SPSS. If you try to do that in SPSS, it takes you directly to the variable view. So each row in SPSS corresponds to a column, the associated column in the data view. So as you see, we labeled the first column age here. We indicated what type of variable age was, and age is obviously a scalar variable. And it's important to do this as well, because whenever you're doing an analysis, it helps you keep track and helps you ensure that the type of analysis you're doing is correct. Because as I mentioned at the beginning, the type of analysis you do often depends on the type of variable you have. So usually if you mess up here, probably the ultimate statistical test you might choose may end up being wrong. So it's just very important from the beginning to have all your data organized and labeled in the correct format. And you see here I have gender. Gender is a nominal variable. When you have nominal or ordinal variables, if you click on value, you can input what each category means so that you don't lose track, right? So as I said, 0 stands for male and 1 stands for female. If you don't label your variables, it becomes very difficult to track later. SPSS will run the analysis if you don't put the value labels. However, you may lose track in a regression, or won't know exactly what you put there. So it's important, if not, you don't have it recorded in SPSS, make a legend for yourself. And in the same way, I have a Likert scale type variable here, with how much 1 likes ice cream, with 1 being not at all and 5 being very much. And obviously I labeled it as ordinal here. So that's what the data looks like. And once your data is set in SPSS, then a lot of the things you end up doing is just under the Analyze menu, right? So just for those that weren't here, I'm not going to go through it detail by detail, because we just have limited time. And we talked about this in previous webinars, but you can do descriptive statistics, frequencies, the number of time, maybe a Likert scale type variable occurred, how many 1s do you have, how many 2s do you have? We have this explore option where you can hit plots, and if you hit normality plots with test, that will give you your result for your Shapiro-Wilks test, your data normality test. And going back what I was talking about earlier, when you're doing a correlation analysis, specifically in a case, the special case where you have 2 variables that are scalar and you want to try to find an association, you hit analyze, correlate, bivariate. You put whatever 2 scalar variables, in this case, we only have 2 here, that you want to analyze, and then you click either Pearson or Spearman. And we do Spearman versus Kendall-Tau because Spearman is more well accepted in the literature than Kendall's Tau. So Pearson, again, SPSS is not going to tell you which one to use. After doing the Shapiro-Wilks test, you will have to indicate which one you're going to use, whether it's Spearman or Pearson, depending on the data normality. And once you hit OK, you can hit your p-value, whether you want it to be 1-tailed or 2-tailed. Reminder, your 1-tailed p-value is just half of your 2-tailed p-value. Once you hit that and you hit OK, you get the output that I was showing you in the slide. So I'm going to stop sharing and go back to my slides. So whatever variables I was correlating here, this is what the output looks like. So as we can see in the first analysis, the Pearson correlation returned a coefficient of negative 0.48, which is, I believe that's a negative but moderate association. But our p-value here is 0.335. That means there's no significant association. So that's what you would report for that in a paper. And for Spearman's rho, this is your output. For whatever 2 variables you were correlating, our association which was negative 0.371, and which I don't remember all the breakdown on the top of my head, that's probably low correlated or close to low correlated. And that p-value is also 0.468. So that also probably means that these variables have no association with each other. So doing that analysis, if you have the right circumstances, can provide a lot of interesting output, especially if you're doing an analysis to see does a certain type of variable increase over time or decrease over time. This is the kind of thing you would do. So now we reach the case of multivariate or multivariable regression. You see this the name used in literature alternately. Some people say multivariate, some people say multivariable. That's why I put both terms here. This is the special case where you have exactly 1 continuous or scalar dependent variable, whatever that may be. It could be height, etc. but you have multiple independent variables. So this is different from that previous scenario we just discussed because we had exactly two variables we were correlating, an independence or X variable and a dependence or Y variable, one dependent or Y variable. This is the specific case here where you have exactly one dependent variable, but multiple predictor variables. And this is what we see a lot in the literature because we know a lot of the things we look at, mortality, etc. There's a lot of things that may predict that. There's a lot of confounders, not necessarily just one thing. So this is why we see this used a lot more under the right circumstances, obviously. And the independent variables that you put into the model can take any form. They can be continuous, nominal, or ordinal. The model is not picky in that manner. So when you ultimately conduct the multivariate regression, what happens is the outputs will help you determine whether and how the independent variables are associated with that one dependent variable. And those associations are represented by p-values and adjusted odds ratios. Again, this was discussed in the last webinar, so this is why I'm just showing it like this here as a recap. So when we did our regression in the last webinar, we had our dependent variable as the length of a car, because that is, and this is a completely nonsensical model, obviously. It's something I created for example purposes, not meant to have any association. The car length is obviously a scalar variable, and these were all the independent input variables. And I'm spending some time on this because you'll notice like this pattern being repeated through every single model that we're going to do later. It's like essentially almost the same way you interpret the output. It's just a different type of model you're using, which is dependent on the type of dependent variable you're being exposed to. So here we go. On the left side of our screen, we have all the independent variables that we put into our model listed here. We have our beta, we have our significance, which is our p-value, and we have our 95% confidence interval for our beta. And these are, the stuff we generally see reported in paper, so it's good to know. Our beta essentially tells us how much the dependent variable would increase for a 1 unit increase in the independent variable. So if we were looking at age, we would say for a 1 unit increase in age, car length would increase by 0.117. That is the point of our beta. And then we look to our p-value. Is that association statistically significant? Our p-value says no, it's 0.23. So it's essentially no. And as we see from this model, none of the independent variables that we put into this model are statistically significant. Also, reminder that once we run our regressions in SPSS, it's also important to look at the model fit. And I discussed more about what the model fits are and what they look like for multivariate regression in the previous webinar, and essentially how to interpret those model characteristics, such as what percent of variance is represented by in the dependent variables represented by our input independent variables. So it's always important to look at model fits and just as well before you just blast a multivariate regression into your paper. It's important to understand all these things. The other thing I forgot to mention last webinar that I want to bring up, but it's like much beyond a basic stats webinar, but I want to get our because it's very important, is that whenever we're selecting independent variables, we have to make sure that they're independent of each other, which is why we have output in SPSS called collinearity diagnostics to help us determine whether our independent variables are dependent on each other or not dependent on each other. Otherwise, that may affect the model fit. So we've discussed two cases so far where the dependence variable was scalar or continuous, but there were different numbers of predictor variables. Now we have a special case when, again, we're dealing with continuous or scalar dependent variables, but now we have two dependent variables, not just one. And when we do, that's what in the literature, people use something called a general linearized model. It's a special case when you have two dependent scalar or continuous variables and multiple predictor variables that can take on any form. And this is what it looks like to set up in SPSS. You see I have more than one variable here in my dependent variable slot. And then I have my fixed factors, which are essentially my variables that have multiple categories or can take on multiple categories. And I have my covariates, which are my other scalar variables, scalar continuous variables. And I have these instructions listed step by step on how to do them in my slides. And this is true for all of the previous slides that I've shared in that Google Drive. All the procedures that we've done, I have it listed step by step on how to do it in SPSS there. So you can always use that for your reference. Okay, so now bringing everything we just said back together, and I don't regret spending some time on what we just spoke about because it's going to help carry the rest of the conversation. It'll make understanding SPSS and what we're going to do easier. So again, I broke up the type of regression analyses by the type of dependent variable. And I think that's the best way to think of it and understand it. Otherwise, you're looking at the statistical analysis section in the paper, and then you're like, they used a Poisson regression. Why did they use a Poisson regression and why they didn't use a multivariate regression? Like, I'm so lost. I don't know what to do. And essentially, this is the dogma. This is basically what it is. They didn't use a Poisson regression because they wanted to feel like it sounds more important or it sounds better. They used it because that's the appropriate regression to use when you have count data. So similarly, when you have continuous or scalar or dependent variables, the types of regression you use, again, depend on the number and type of dependent and independent variables you have. And what we discussed in the last webinar was essentially the first bullet. And that's what we just went over. For continuous and scalar, it's linear regression for exactly one dependent, one independent variable. Multivariate regression for multiple independent variables, but exactly one dependent variable. That's scalar or continuous. And general linearized model for exactly two dependent scalar or continuous variables and multiple independent variables. So in this session, we're going to tackle the remaining three, which are nominal dependent variables. What types of regression analyses do you use then? Ordinal dependent variables, and when you have count data. And when I say count data, I mean like that type of data where you're talking about number of deaths or number of adverse events. And I'm sure you guys in your journal clubs, etc., you've seen a lot of that. They had like number of deaths, number of events, and then they modeled it with the Poisson regression to see what were the most important predictors. Okay, so when we're dealing with the case of nominal dependent variables, there are two different types, right? There's your binary logistic regression or binomial logistic regression, and then there's the multinomial logistic regression. And a lot of the times, a lot of this sounds a lot complicated to remember, but it's really just intuitive. And what I mean by that, when you break apart the word binary or binomial, what does that mean? It means two, right? So it simply means in this case, your dependent variable is nominal, which means it has, if you remember what I mean by nominal, it takes on categories, right? But it takes on exactly two categories, binary, binomial. So in this case, we're looking at the type of logistic regression you use when you have a nominal dependent variable that only takes on two values, which could be yes or no, or true or false, etc. But it can only take on two values. Your independent variables that you put into that model can be continuous, scalar, nominal, ordinal, whatever fashion, it doesn't matter. The dependent variable, you want to make sure that you label, whatever the outputs mean, the 1 or 0 or true or false, etc., in SPSS, so you remember exactly how to interpret your results. But remember, again, for binary logistic regression, your dependent variable is only taking on two values, no other values. So otherwise, the analysis won't run correctly. All right, so this is the steps. This is how you do this in SPSS. So I'm going to stop sharing my screen, and we're going to do the binary logistic regression in SPSS. So this is my SPSS screen. If you notice, I have several variables here. There's only two of them, which you guys see are binary, which is gender and whether or not a person likes ice cream. Obviously, I'm not going to put gender. I'm not going to use gender as my dependent variable because gender is an independent variable. I'm going to use whether a person likes ice cream, where 0 represents no and 1 represents yes, as my dependent variable. And we want to determine whether of any of these things, which are all nonsensical, by the way, it's just I threw something together, whether any of these things are good predictors of whether I like ice cream. So in order to do that, I'm going to hit analyze. I'm going to hit regression. I'm going to hit binary logistic. My dependent variable is whether I like ice cream, and my covariates are everything else. Now, again, this is Biostats Made Simple. I'm not going to get into more technicalities here, but I just want to bring your attention to a few things. In the case that, you might want to adjust for variables or put things in different blocks or do like a stepwise regression. All you have to do is use the method section here to select what kind of type of regression you want to use. And if you click on the next, like you can select how you want your variables to go in. Like if you want to control for age and gender, you'll put for age and gender as your first block. And then next you can put all your other variables that you're not sure about. So like, that's how people like design like a hierarchical logistic regression. But for simplicity, I'm just going to show you guys how to do it here. And whatever I show you guys today, you can take it and build off of it. Let's just explore whatever. Okay, so here we have to define our categorical variables. And our categorical variables are gender, car type, and how much ice cream. And then I'm going to hit continue. Options. You always want to click on how much or let me show goodness of a fit. Because as I always say, we just don't want to do a model just for doing it. We want to ensure that the model is good. Otherwise, reviewers will come back and say, was the model good? Like this model doesn't make sense. That we just want to make sure that, the model is good. And this is the way to check the hamster. Let me show goodness of fit. You want to do your confidence interval for your exponent B. Your exponent B is your odds ratio, which essentially magnifies, or not magnifies, but it tells you how important your independent variable is in predicting your dependent variable. And you can click off whatever you want here. But these are the most important things, your iteration history. I'm going to click continue and I'm going to hit OK. Now, I know sometimes people have trouble seeing my screen when the output comes out. So I'm just about to stop sharing right now and I'm going to reshare the screen to make sure people can see it. All right, so this is the output screen. As you see, SPSS outputs a lot of things. Some things you care about, some things you don't care about. But what's most important is what I want to bring your attention to here, the Hosmer and Lemichaud test, which essentially tells you how good your model is, not essentially how, but whether your model is a good model, essentially. And if the p-value is greater than 0.05, yes, your model is a good model. If it's less than 0.05, it's not a good model. So we see here our significance, that's how SPSS labels p-values, is 0.68. That means that the model is a good model. Whether it makes sense or not, it's a good model. Then also, maybe you should also look at your model summary, where you have your Nagelkerke R-square. And what this essentially tells you is that 35.2% of the variance in your dependent variable can be explained by the independent variables that you put into the model. So 35%, while it's a good model, 35% is not that great. But then again, we realize that we don't live in an ideal world. And a lot of the times we don't have all the variables that may necessarily be predictors of the dependent variable. So sometimes we just have to work with what we have. But, when you're publishing a paper and stuff and like trying to interpret your results, these are good things to remember. And then we want to look at our outputs. Let me find our output. So this is our outputs of the regression. It says variables in the equation. We have all our independent variables listed here. And if you see, like, for example, how much I like ice cream from 1 through 4 and car type from 1 through 4, 1 through 4 represents the different categories that we input because these are nominal variables, right? So if you remember when we were talking about how much I like ice cream, 1 represents not at all, and 5 represents a lot. And 5 is not listed here because SPSS by default used 5 as the reference category. Now, just one bit about reference categories. Reference categories could be whatever you select them to be. And depending on the intent of your study question, your reference variable could be something you're not interested in, or the most occurring variable, or the least occurring variable. The idea is you want your model to only output variables or the things that you care about. So essentially, I wish I had a more scientific answer, but like if you look through the literature and stuff, reference variables are essentially whatever you choose them to be, depending on what you want your output to look like, whatever your results you care about. Because obviously, if you cared about like what was predictive of someone like really liking ice cream, then you wouldn't put that as your reference category. You'd probably put like 1 or something to see whether it was significant or not. And then you see we have our significance here. These are our p-values. So it tells us the contribution, not the contribution, but whether or not each of these variables are significant predictors of our dependent variable, which was whether or not we liked ice cream. So just full disclosure here, if overall car type is not a significant predictor, then you do not have to bother to look at the individual categories. So you just state that car type was not a significant predictor of whether I like ice cream. However, if this p-value was statistically significant, then you would have to further look at which of these categories, 1, 2, 3, or 4, which of these are also statistically significant, which contribute to the significance of car type being significant. And let's see, the 95% confidence interval here is for this exponent beta. This exponent beta is something you would also report in your paper. This is your adjusted odds ratio. And you've all heard of odds ratio. What do I mean by adjusted odds ratio? Whenever you have an output from a regression model, and obviously this is an odds ratio, but the reason why it's called adjusted, it's simply because it's taking into consideration the fact that we're adjusting for different independent variables here that also may have an impact on the dependent variable. Therefore, it's called an adjusted odds ratio. So we see here that, let's pretend for a second car type a p-value was 0.02. That means car type is a significant predictor of whether I like ice cream. And then we find that there was a specific car type that kind of drove that significance, which may have been a Honda. I believe one was a Honda. And then my odds ratio for that, as you see, was a whopping 12.2. So we see that, our odds ratio tells us the magnitude of that significance, right? So clearly that, not only was the result statistically significant, but, the type of car that I may really have an impact on whether I like ice cream. And then this is the 95% confidence interval is the confidence interval for that adjusted odds ratio, and so on and so forth. So that's essentially how you would report the results of a binary logistic regression. And this is like the same pattern that carries throughout for all the other regressions I'm going to show you. So you just have to keep your eyes on your variables that you put into the equation, your p-values, and that adjusted odds ratio and its associated confidence interval. So I'm going to stop sharing this and go back to my slides. So as I said before, this is a handful to listen to, and all you guys know, or you may not know, but you will now, all of these recordings are pre-recorded and they will be on, YouTube or the SAEM website. So you always can go back to them and refer. Also, just a reminder, I shared my slides in the chat, which has all these steps listed step by step, so no one will forget how to do them. But once you understand the pattern, it should be easy to catch on. Okay, I see a question. Why is the overall p-value for car type not significant, but there are individual ones that are? So the way to think about this, right? We're going to act like, and I wish SPSS, remember, SPSS does not think like a human. Like, just like I was giving the example for like the Pearson and Spearman, it gives you both options, right? But at the end of the day, like if you click Spearman, although that's wrong, it'll still give you an output. So like, it does not think like humans. And so the way I would explain it is that if SPSS was like AI and it had the intelligence, advanced data, I would say, it had the intelligence to realize that it shouldn't output p-values for something that's not overall statistically significant, it wouldn't. So that's the best answer I would give you. So SPSS will give you p-values, but it's just up to us to interpret whether we should even look at that p-value or whether that p-value is relevant in other way. I don't know their backward, like how they work on thank you so much, in the backgrounds, why it's like that, but that's the way it is. Technically, if it was on me and I was designing SPSS, like for anything that's not significant, all those different categories, like I wouldn't even show those p-values. Alrighty, so thank you. Alrighty, so again, I have the setup here, screenshots of the setup, then the outputs, just a reminder to look at the model fit diagnostics. And now we're in the case of the nominal dependent variable where we have a dependent variable that has multiple categories, that is greater than 2 categories, and multiple independent variables that could take on any form, nominal, scalar, or ordinal. So like, what are examples of variables that can take on multiple categories? Maybe color, right? Which yellow, green, red, etc. But obviously we don't put yellow, green, red, etc. into SPSS. We can put in our values column, but we have to label it in SPSS language, like 1 represents yellow, 2 represents green, 3 represents red, etc. Type of car could be another multinomial logistic regression dependent variable, right? Because there's several types of cars, unless you just want a model looking at 2 types of cars. So let's just show you guys how to do that. And obviously, once you guys start doing like one on your own, you're just going to start intuitively figuring out how to do this. because SPSS speaks in the language that we understand it. So obviously, if we go to analyze, because that's what we're going to do, we're obviously looking for a regression. And then all the types of regressions are listed here. So if we want to do multinomial logistic regression, it's clicked here. And again, if you don't remember what type of regression to use when, just kind of remember, think of it intuitively. What kind of dependent variable do I have? Do I have a continuous or scalar variable? Do I have a nominal variable? Or do I have an ordinal variable? And once you conclude that you have a nominal variable, because your variable has several different categories and takes on several different values, but it's greater than 2, obviously you're going to go to multinomial logistic regression and not binomial logistic regression. So I'm going to click on multinomial logistic regression, and I'm just like eyeballing my variables right here. I'm trying to figure out which one is nominal and has multiple different categories. And the first one that comes to my eye is car type. So I'm going to move car type to my dependent variable. And I'm sure you guys can start seeing the pattern. No matter what you click for type of regression, it's the same concept over and over again. You just have to make sure you click the right one. And then SPSS sometimes will alert you, like they'll say that, this doesn't make sense, but that doesn't always happen. Your factors, again, are things that can be variables that can be broken down into categories. So that also includes your ordinal variables. Your covariates are your scalar or continuous variables. And let's see, model, I care about that here. Stats, we want our goodness to fit. So we're gonna make sure we click that. You can click whatever you want here. Let's see, options. I'm gonna hit okay. And then I'm gonna stop sharing and reshare to ensure you guys can see my results screen. This is just some descriptives of the data. Again, we wanna look at our goodness of fit diagnostics. Here, when Pearson is less than 0.05, it means that the model is a good fit. It means that it would do better than a model than if you just had an intercept alone. Clearly, we see here that P is greater than 0.05. So it means that this model is probably not the greatest fit, and we don't expect it to be because I put a lot of nonsense variables in there. Then we look at the pseudo R-squared box. That essentially tells us that, looking at the Nagelkirche, approximately 52% of the variance in our dependent variable can be explained by the independent variables that we put in, which is not bad, but it's bad because the model wasn't good to begin with. So that being said, it's important to keep that kind of stuff in mind. I'm going to scroll down, and we're going to look at this table called parameter estimates. And if you notice, it's like, again, it's designed the same way as all our other regression tables were designed. But the difference is that if you notice, under car type here, we have each of the categories of our car type. Remember, this was a multinomial logistic regression. So our dependent variable had multiple categories. So we had multiple car types, right? So I had a Honda here. And this is the importance of labeling the variables in the variable view. Otherwise, you'll just have 1, 2, 3, or 4, or 5 without knowing what each of these variable types represented. So I have a Honda here, and each of the independent variables and what is their association with that dependent variable. Then I have the BMW with the same thing, each of our independent variables here, and what that association is with, being predictive of whether or not somebody got a BMW. And we have Mercedes here, same concept, each of our independent variables and how predictive they are of the Mercedes, Porsche, so on and so forth. So again, this is the specific case. You use the multinomial logistic regression when you have a dependent variable that has multiple categories that is more than 2. Output, you interpret it the same way. You look at your significance, that's your p-value, right? And we see a lot of nonsensical stuff here because obviously my model doesn't make sense, but we see, if we go here, let's just stop here at ice cream, for example. So it took here, like ice cream, as yes, as my reference category. So it's giving me output for no, I don't like ice cream. And that p-value is statistically significant, 0.04. And so what does that mean in context of the problem? It essentially means that if I don't like ice cream, that's predictive of me getting a Honda, which makes no sense at all. But you guys get my point. That's how you would interpret it. And we see that if this, in fact, did have some important association, we see our exponent B, which is our adjusted odds ratio, is humongous. It's 21.7. So not only is that association statistically significant, but apparently if I don't like ice cream, that apparently is a huge predictor of whether or not I get a Honda. And then this is my associated confidence interval for that exponent B. So that's very important. And you would interpret your other results, so on and so forth. just want to bring you a quick note before I move on to the next regressions, is that when you're running your own regression, right? And you see nonsensical stuff like this, a really huge adjusted odds ratio and a confidence interval that's essentially like zero, it could mean that something's wrong with your data or there's missing data. So it's always good. It goes back to that nitty gritty of like looking at your data in Excel and determining whether or not your data is appropriately coded, etc. If you look at my previous videos, you also see that SPSS has a place for you to indicate whether data is missing and how you've coded that. So these are essentially red flags for interpreting your data whenever you see numbers like that. And only recently I've had to run an analysis where I noticed things like this. And then I've had to rerun models several times. In fact, I had to take a different model approach, like a stepwise regression, so that, it eliminates predictors. That's another reason why sometimes you get nonsensical results. If you have too many predictors in your model, obviously SPSS is going to give you output, but it's going to give you output like this. So when you do something like a stepwise regression, backward or forward, it helps you eliminate some of those variables that it doesn't think might be predictive, and it'll help you produce a cleaner model. So that's just something to keep in mind. All right, let's go back to the slides. So again, all steps listed here. So now we're in the special case where we have a dependent variable that's an ordinal variable. That means it can take on, Likert scale type data, like data that's not nominal in that it takes on an order, right? Like 1 through 5, or if it's like grades A through F, those types of variables take on an order. So if your dependent variable takes on an order, it's an ordinal dependent variable. And there's actually something called an ordinal logistic regression for those types of scenarios. And like, I think people can easily relate to this because, yes, we do collect Likert scale data type from our medical students, etc. But we might want to examine what are predictors of somebody rating something a 5 on a particular question versus a 1. And that's when you might want to do the appropriate regression, which is not multinomial logistic in this case, because these types of variables take an order, but it's something called an ordinal logistic regression. And again, this is simply how you would do it in SPSS. And I know we are getting out of time, so I'm just going to show you guys how to do it really quickly, but it's the same process as we've done before. So I'm going to hit my data set. We're going to go to analyze. We're going to go to regression, and we're going to go to ordinal. Our dependent variable, we only have one ordinal dependent variable here, which is how much do you like ice cream on a scale of 1 to 5. Our factors are our gender, car type, and ice cream. Our covariates, and car length. And it's essentially the same process every single time. I'm going to hit OK. I'm going to reshare to make sure you guys see my output. Again, you look at your goodness for fit. Pearson is greater than 0.05, so obviously this is not a good fit model. Had it been, essentially 6.5% of our dependent variable would be explained by the independent variables we put in. And our output looks like this. And again, it's the same exact concept. So we have our p-values here, and we have our 95% confidence intervals here for our parameter estimate. So it's the same concept, and you think of this ordinal one more like the multivariate regression, where we look at kind of like our beta versus our binary and our multinomial logistic regression. So just like as a reminder for our interpretation, you can always refer back to that previous webinar. But again, it's the same concept. You're looking at either your adjusted odds ratio or your beta values, and you're looking at these confidence intervals, and that's what you report on your paper. And never forget model fit. Okay, let's go back to the slides. So I'm not going to physically do an example for this, but it's the same concept. So for counts data, that's for data for like, what I was saying before, if you have like number of adverse events or number of deaths, you would use a type of regression model called the Poisson distribution. So it's, again, strictly used when your dependent variable represents a frequency or number of occurrences. There's a question, is the factor box only for independent categorical variables, either nominal or ordinal? So the factor box has all of your input variables that you put in. The factor box, when you're designing your model, that's only for ordinal and nominal variables. Only for those. It's any type of variable that has categories can go in the factor box. Covariates is only for scalar and continuous variables. So that should be fine for that. You're welcome. And then this is just a reminder, again, that the type of model we choose depends on the type of dependent variable. So for counts, it's going to be a Poisson regression or negative binomial distribution. And dependent variables can take on any format. And when I say either Poisson or negative binomial, that's something you won't know until you actually run the Poisson distribution. And that's just like, there may be more technical ways to figure that out, but I feel like this is the most simple way for people to figure it out. Once you run the Poisson distribution using the following steps, and I'm about to share that really quickly, we're towards the end. This is how you would run a Poisson regression. You would hit Analyze, General Linearized Models, Generalized Linear Models, and then you would literally select Poisson here. And then you just put your factors. It's the same process over and over again. Your factors are your scalar and continuous variables. You put your factors there, your covariates here. For statistics, you have to make sure you include your exponential parameter estimates. Oh, your response, you have to include whatever your dependent variable is. And I don't have a count type here, but like if it was number of adverse events, that would be your dependent variable, and you would just move that here. Then you would click OK. And let's go back to my slides. So again, the thing is listed here. And the output looks exactly the same as all the other outputs that I've shown you before. You have to remember, again, to look at your model fit. If the Pearson, in this specific case, there's different model fits essentially for like all the models. As you know, with the binomial logistic regression, I introduced you to the Hamster-Lem show, but that's not something you would use for like the multinomial logistic regression. But for the Poisson, if the model fit is measured by the Pearson chi-squared, if that goodness to fit number is close to 1, then you know the Poisson is a good fit for that model. And if it's not close to 1, if it's significantly greater than 1, then you should try running the negative binomial regression. And on that same screen where I showed you how to click Poisson, that's the same screen. Right on that screen, you can click negative binomial. And you would run that. And then you would look at the same thing, Pearson's chi-square. If the chi-square is close to 1, that means the negative binomial is a better fit than the Pearson chi-square. Other things to look out for. The other outputs you get from SPSS for the Poisson and negative binomial, that relates to model fit. There's also something called BIC and AIC. And these are usually humongous numbers. Sometimes they're in their 10,000s, 20,000s, etc. The model that has the lower BIC and AIC, that is the better model. So again, you're looking for two things when you're looking at Pearson. You're looking for goodness of fit. You're looking for the Pearson, and you're looking for a low B1C and A1C. Once you determine what is the best model for your count data, if it's a Poisson or it's a Pearson, then you can go on to further interpret your parameter estimates. That's your results table, which looks like all the results tables I just showed you. But again, one thing I want to point out, it says exponent B, but you wouldn't interpret that in this case as an adjusted odds ratio. It's called something called the incidence odd ratio. So that's just what makes that different from all the other models we talked about. So every model, essentially, it's based on the same concept, right? The type of model you select depends on the type of your dependent variable and sometimes the quantity of dependent variables. And there's several things you have to remember. You have to remember to look at model fits, collinearity diagnostics to make sure your independent variables are independent of each other. You have to remember to look at your p-values to make sure those significance are association. Associations are significant. And why I say that, you may look at the table and see, and the first thing that strikes you is like, oh my gosh, that adjusted odds ratio is huge. That means my independent variable, this particular independent variable, has a very large impact on the dependent variable. And this is a groundbreaking discovery. And then I point you to the significance, the p-value, and it's like 0.381. And I say, no, that's not true because the p-value is not statistically significant. So when interpreting the results of your table, you have to be very careful. You have to ensure that, number one, your p-value is statistically significant. And number two, you have to look at the adjusted odds ratio or the incidence odds ratio, whatever it is, or your beta. And you have to look at, if appropriate, if it's negative or positive, if your adjusted odds ratio is less than 1 or greater than 1, and if it's greater than 1, how big it is, and etc. So it's just really important to put everything in context and be able to figure out how you can link your results to your dependent variable. Also, just a review again. So, one can rote memorize this, but once you understand it, like it just becomes intuitive. For your scalar and continuous dependent variables, the type of regression models you use could be your simple linear regression or your Spearman's row analysis. your multivariate regression for multiple scalar, your multivariate for multiple independent variables, but a single scalar dependent variable, or GLM, general linearized model, for two dependent variables that are scalar or continuous and multiple independent variables. For nominal dependent variable, you can do a binary logistic if you have a dependent variable that takes on two values. And if it takes on more than two variables, then you do multinomial logistic regression. For ordinal data, such as your Likert scale data, you can use the ordinal logistic regression. And for count data, you use either the Poisson regression or negative binomial logistic regression, depending on the model fit. And just remember that your exponent B is either your adjusted odds ratio or your incidence odds ratio, depending on the model you're using. And remember to look at the p-value to determine whether that adjusted odds ratio is significant or not. And also, whenever you're reporting your results, to report it in a table when you're presenting this to reviewers, because they're not just looking for p-values. They want to see the, like, what impact does this variable have on your model. And that was pretty much it. Thank you. I hope that was helpful. Thank you for the kind comments, and thank you for the excellent questions. Thank you guys for coming, and I hope you had a wonderful session. Please review these videos. I hope they're helpful, and looking forward to seeing you next month. Thank you. Have a wonderful day.